I'm Sean Sullivan, and why don't we immediately get into the tasty nougat of the presentation with a kubectl port forward and kubectl exec demonstration. So at the beginning, I'm just going to show that there's what the client and server versions are and what's running, the workload that's running in the cluster, just to give us an idea of how this particular cluster is set up. We've got an Nginx workload running in our cluster. And the first command that we're going to actually look at is kubectl port forward. So when we run a kubectl port forward command, we're creating a long-lived streaming connection between the client and Nginx in the cluster. So with the command, we're going to specify what the local port is, as well as what the port is that Nginx is going to be listening to in the cluster. So I'm going to make this a verbose command so that we could see what the headers are for this particular command that we run. And you could see that we're specifying a particular sub-protocol that we're interested in. So that's the endpoint. The protocol that the client wants is the port forward.k8s.io sub-protocol. And then there's going to be a handshake with the Nginx process to determine what particular sub-protocol is agreed upon, and if it's successful, it returns 101 switching protocols. And so now we have a long-running streaming connection between our client, our local client, and the Nginx process running in the cluster. And so in a separate shell, we're going to run a curl command to request basically the home page for Nginx. And we do it by contacting local port 8080, and that's going to be forwarded through that streaming connection to Nginx. And so you could see that we got the home page there from Nginx. And so why don't we move on to exec commands? And so we'll do a really simple one initially, which is we're going to do an exec. We're going to run the date command on this Nginx process. And so I've made it verbosity level 7, so we're going to see a lot of headers, a lot of header information here. And what I want to point out is not just the endpoint, but we get to specify as query params what the command is, what container we're talking to, as well as some of the channels that we're going to need, which is standard out and standard air. And in the request headers, we're saying that we support multiple versions of a sub-protocol. And this is the remote command sub-protocol. We're going to get into that in a minute. And the response was 101 switching protocols. Great. You could see that actually at the end there, we had the date that came back on the standard output and was shown. Okay, so this is an involved example in which we're going to show that this particular command, when we've created this streaming command, we can send stuff through the standard input channel and receive stuff on the standard output channel. And we're actually going to send 50 megabytes of the kubectl binary on the standard input channel. We're going to echo it onto it. And then at this Nginx, we're just going to cat it. We're just going to send it back down on the standard output channel. And then we're going to redirect it into a temp file, and we're going to say, well, did this particular binary, this massive amount of data, did it come back as the same data? And so So right now we're just looking at, so this is the command, the kubectl exec command. We have to do the -i, we have to do -i because we're using the standard input channel, and we're going to redirect it into output.kubectl in the temp directory. And so, okay, we've done that. Let's have a look at that, what we received, and it looks like it's the same size. Let's just do a diff to make sure that that data we sent to Nginx and received back is the same, and it is the same. So finally, let's execute a shell. So this is a really useful debugging tool that we could use. Is we're going to jump onto the Nginx process itself. And so when we run, and we're running bash, so who am I running as when I jump on this shell? Well, I'm root. When I'm there, I could look at the error log, I could look at the access log, I could look around. And so this is a very useful debugging tool. So, oops. So what is it that makes these particular APIs different? These two particular commands we just saw, they're streaming commands. What does that mean? What is that? How is that different than HTTP? Well, most of us know that our Kubernetes exposes an HTTP REST API. What some of us aren't as familiar with is that there are actually this small subset of APIs which end up being upgraded to streaming connections. And we just exercised a couple of those APIs in those commands. And so we're all pretty familiar with what HTTP is, but why would we have streaming commands? Well, it's basically the deficiencies of HTTP, which is a request response protocol, just aren't going to be sufficient if we're running and interacting with a shell that's all the way in a cluster on a particular workload. And so here's a couple of the characteristics of the streaming protocol, or the streaming dynamic, which make it more useful than HTTP REST in some situations where there's low latency, it's less bandwidth. For HTTP, you're going to have headers that for every single request and every single response, you're going to have can be significant header overhead. Whereas in streaming protocols, we're framing usually binary data with very little metadata. And with streaming, it's important to note that either endpoint can initiate these data messages, and it's bidirectional. Let's see. And so the example, which I think illustrates the best that these streaming protocols are necessary, these streaming APIs are necessary, was this interaction with a shell on the container. It's just not going to be possible to have that type of an interaction if you have to do it through request and response. Okay, so how do we create this streaming connection? Well, we start off as an HTTP request, and this is kind of a truncated version of what the request looks like when we're trying to do an exec. And we have a couple of extra headers. So we're going to say we want to upgrade the connection, and our streaming protocol is going to be Speedy 3.1. And these are the particular sub-protocols that this client supports. And it's a priority order. So V4 means that we want V4 over V3. And I'm going to get into what a sub-protocol is shortly. And so after the handshake, if it's successful, then the HTTP response is going to say 101 switching protocols. Okay, that worked. And these two particular headers are going to be spit back at us, the same that we sent to them, and the negotiated sub-protocol, which in this case is the v4 version of remote command. Okay, so what are subprotocols? So subprotocols are the what of what's going into these data, the payload of these streaming messages. They're versioned, and Kubernetes defines two subprotocols. So we define remote command, and this is for the following three commands: kubectl exec, kubectl copy, and kubectl attach. Kubectl copy actually is implemented through the exec endpoint, so it's kind of the same as exec. Attaching is attaching to a running process, but each one of those three is going to require, it's going to take advantage of this exact same remote command protocol. And the latest version is version 5. For port forward, it supports the kubectl port forward command, which we saw the example of, and the latest version is v2. So what exactly is in our remote command subprotocol? We are multiplexing up to 5 channels of data. So we've got standard input, standard output, and standard error. That's pretty straightforward. If we're going to be interacting with a command in a cluster, we're going to have those 3 channels. And then we also have, actually, for later versions, we added terminal resizing or TTY resizing events, and we added an error channel which allows us to get the process's exit code. So those channels of data are all going over the exact same streaming connection which is set up and that's being multiplexed over that connection and then demultiplexed and connected to the process that's running in the container runtime. So for port forward, actually there's one thing that I meant to mention here in our remote command example in this subprotocol is that the number of channels is static. It can be up to 5, but it's at the beginning, once it's negotiated, it's going to be the same number. It's not dynamic. Whereas for the port forward subprotocol, it is dynamic. So we set up in the command, in the kubectl port forward command, we set up that long-lived streaming connection, and maybe in a different shell, we're going to do a curl, and we're going to connect to that. Well, the number, when we do that, there are 2 channels for each one of those forwarded commands, and there's a data channel and an error channel, but the number of them, of these channels running concurrently can be infinite. It could be, I mean, obviously there's resource constraints, but it's not defined. If we had 1,000 curl commands running at the same time, then we would have 2,000 channels. And so this actually presents some challenges for how we ended up, I'll get to it, how we ended up proxying the WebSocket, a different protocol to Speedy protocol. Again, I'll get to that, getting ahead of myself here. Okay, so this diagram is meant to illustrate just kind of the end-to-end nature of these streaming connections, these streaming APIs, and they actually touch quite a few elements of the cluster. So they're going to start off with a client, usually kube control. They're going to talk to the API server, which is generally going to just proxy this particular, the request and the upgrade to the kubelet. The kubelet is going to then, through the container runtime interface, proxy to the container runtime itself. So we're talking all the way from the client through the API server to the kubelet on the particular node, and then while you're on that node, we're going to be talking through a Unix socket to the container runtime through the container runtime interface. So there's quite a few components that we're touching in this when we're talking streaming APIs. Okay, so why are we even talking about this? These streaming APIs have been around for years. Well, we're talking about them because we have recently transitioned the streaming protocol from Speedy to WebSockets. And that happened as of version 131. The default streaming protocol for any of those 4 commands that I've mentioned is, and it's defined in that CAP 4006, is now going to be WebSockets. It'll fall back to Speedy if the server doesn't, if the container runtime or the server doesn't support that. But by default, we're going to attempt a WebSocket upgrade connection. Okay, so why did we do this? This is quite an undertaking. It's actually, it started years ago, and we've just recently kind of gotten to a point where it's been published. Well, Speedy's been deprecated for 8 years, actually more than 8 years, and it was never standardized. And so what we get is we get to a situation where even though we control all of the elements within the cluster, there can be some intermediaries, right? There can be some gateways, proxies, load balancers between the client and the API server, between, that don't speak this aging protocol. And so we've gotten to a point where anybody who's using a gateway will probably need to use a more modern streaming protocol, which is WebSockets. So we should note, however, that we've only modified the streaming protocol from the client to the API server. So we've implemented for both of these sub-protocols, we've implemented proxies in the API server that translate or tunnel the WebSocket. For translation, it's from WebSocket to Speedy. So there's a stream translator proxy, and then for port forwarding, there's actually a tunneling protocol. And we did the tunneling, as I mentioned before. For port forward, we have a dynamic number of channels. In order to not blow up the API server, our design required a tunneling translator, a tunneling proxy. And so Speedy actually continues to be within the cluster is the communication protocol. And we did that because we've seen this dynamic before where we have to, if we would have changed the container runtime, then we would have had to have fixed all of the container runtimes. And we've seen that is actually, we've seen that fail several times. And so what we decided was, well, we're going to get 99% of the benefit if we change just the leg between the client and the API server, and we keep the rest of the cluster working the same. We intend to actually move the WebSocket legs all the way through the entire system, but we're starting out with this first leg from the client to the API server. So this is the updated diagram, which illustrates what the cluster looks like. And that purple part within the API server represents the translation or tunneling proxies, which are changing WebSocket back to Speedy within the cluster. So to wrap up, I have a bunch of links here to what I think are very useful resources if you plan on digging in more into this particular topic. I really wanted to point out to one of the blog posts by Sasha Grunert. It goes into an area that I kind of gave short shrift to, which is what happens with the streaming on the node. So between the kubelet, through the container runtime, to the container, that's actually a pretty involved process, and there's a separate blog post altogether that Sasha Grunert wrote that I think would be very useful if you're really interested in want to know more about streaming as it pertains to the node itself. And that is what the Kubernetes, the container runtime interface streaming explained by Sasha. Okay, so looks like we've got about 5 minutes left. Are there any questions? Go ahead, Mark.
Okay. I have maybe a naive questions, but it relates to maybe what I'm trying to do. It's how does streaming cover, watch, or at least the current state of the watch? How does it differ?
So the watch isn't related to the, I mean, so the watch is kind of an HTTP streaming that we don't actually use Speedy or WebSockets for watch.
So it's a complete different implementation because it's not bidirectional streaming, but one-directional streaming.
Right. So HTTP does have streaming, but it's in this overall paradigm of request and response. So it fits within HTTP. Whereas, if you're interacting with a shell on a container, that's not going to be, request response. That's going to be, connecting bidirectional. So I'm actually not an expert on watch. Maybe Han could actually answer better. So watch is still HTTP, right? It's not. We're not using.
I was assuming so, or I'm trying to figure out because there is a pending proposal, or because I'm more now watch on etcd side, and one of the things that was that is discussed is having a bidirectional or a high level, eventually consistent caching, or let's say forced progress notification on watch to get eventual or strongly consistent caching on the informer side.
Right.
So for that you need to have a streaming that watch you need to make a progress, or at least in etcd we call it progress request notifications, which would on Kubernetes side call it a request for a bookmark basically. So that would make it by streaming and not necessarily a request response, because not always you will get an event back, and this is like true on etcd, which also implements a very complicated it's custom streaming protocol. So I was asking in that direction. So
it sounds like, so currently the watch is an HTTP REST call, but if you wanted that bidirectional functionality, then you would have to do, as we were showing before, you'd have to upgrade to a streaming protocol, and it should be WebSockets or something modern, just because Speedy, otherwise it's just not going to be well supported. So that was back here. It was describing this HTTP request. So you're going to have to upgrade to a streaming protocol.
Okay, thanks.
So my concern is upgrading from one version of Kubernetes cluster to another. Yep. If I have 1.30 or 1.31, is this change going to force me to really install new and migrate, or is this change going to be? Can I upgrade in place? I couldn't interpret everything quite to understand.
So that's a great question. So this should be transparent to you. So
okay.
So you may have an older kube control, which isn't asking for a WebSocket upgrade. It's going to ask for the previous Speedy upgrade, and all of that's going to continue to work. And the other version SKU that you may have is you may have like a more recent kube control and an older server. So if it fails, if it doesn't understand WebSocket, then it's just going to fall back to Speedy. And so we...
Oh, okay. Okay. So this is going to be upgradable. Okay.
If it's the same, if you have got a kubectl server, which is 130 131 and the server is 131, then they're both going to speak this WebSocket, and you're going to get upgraded.
Oh, that's what I'll want in the long run, but okay, gotcha,
Yeah,
thank
but
you.
it should be completely transparent to you. There's
right.
nothing extra that you need to do as a cluster operator or a kubectl user.
Thank you.
So when I showed the demo, we had I showed that we were at 129, and I did that so that that was when we had Speedy both in client and in the and the server, and so that was for years and years that's how it worked, and so it's only recently that we've begun to do this particular implement this particular functionality, and so I wanted to show how it worked before I said, okay, well now we're going to do Speedy.
I have a deep dive question.
Sure, go ahead, Machi.
For the TTY resize, why we need that one particularly for the remote command?
So my understanding is because of that last example of when you're running a shell, and so it could be that. I haven't seen that often, but it's if your shell on your client changes size, then you may need to communicate that to the process because it thinks that it's has a particular size, terminal size. Yeah. Yeah. But that is a deep dive question. So that was introduced in version 4 of the remote command protocol. And okay.
I just looked it up. I was like, I didn't know we had different versions. And
Yeah.
that's because they were all made in the very beginning.
And so version 5. Yeah, so version 5 was the one that we just introduced, and we had to introduce that because on the server side, we didn't deal with standard input correctly. So there was no half-close signal that signified that the standard input channel was finished, and so it would hang. And so we've recently implemented that half-close signal to signify when standard input is finished.